Oh, okay. I can hear you now. Thank you so much
Fantastic.
for confirming that. So can you see
Absolutely.
my lecture slide?
Yep.
Okay. So what about my headset? Is my headset working?
It should be. If you can hear me, we can hear you super
Okay.
clear, and we're able to see the
Okay.
slides.
Okay. Thank you so much for that.
Absolutely.
Yeah. I want to welcome you to my lecture today. Today, we actually going to continue from chapter 3 that I call discrete probability distributions. And of course, the focus today is basically going to be on Bernoulli distribution, binomial, and geometric distribution. But before I get started today, I actually need to make an announcement about this is analysis of midterm one results for both 4101 and 5101. You know, exam, people will say election has consequences, right? As a result, exam also has consequences. By now, if there's anyone who really sees struggling in this class, I think by now you know what to do by meeting with me during my office hour. My office hour start from 11:30 a.m. because my lecture end at 11, and of course it's 11:30 a.m. So this is not too good, not too bad. Even though I was targeting the minimum to be 99, so but it's not too bad. But there's always room for improvement. Okay, so that is the analysis of you know midterm one. Okay, so let me just prepare your mind. In the syllabus I said the I was going to give a detail about how the midterm one, midterm two, and the final exam will be conducted. The opportunity in midterm one will not be in midterm two. In midterm two, even though if I'm going to allow exam to be on for 24 hours, just like the way we did. When you want to write the exam, you're going to log on to Zoom, even though I'm not going to be in the Zoom, but the Zoom will automatically record you with your video on. But there's going to be information about that as time goes on. Okay, so let me go back to what we want to do. Like, I need you to pay attention now to what we want to do because we'll be going mathematical, more mathematical. Because when I talk about properties of Bernoulli, binomial, and geometric distributions, that will require us to go more, mathematical because we're going to be deriving some stuff. But you know what I want to do now? I'm going to use 30 minutes to walk you through the essence of Bernoulli, binomial, and geometric distribution with examples. Then before I will now actually make a derivation, a theoretical derivation of some stuff. Now the other time I introduce you to binomial and Bernoulli. Of course, I said Bernoulli distribution. The whole idea starts from Bernoulli distribution. The Bernoulli distribution has when you perform one trial and there are two possible outcomes. I'm going to say that again. One trial, two possible outcomes. Okay, that is Bernoulli distribution. But for binomial, you perform more than one trial, but you still have two possible outcomes. You can see the difference between the two. Bernoulli and binomial distribution actually have two possible outcomes. The only difference between Bernoulli and binomial distribution is just like the numbers of trial in Bernoulli is one. The numbers of trials in binomial is more than one. That is just it. The other time I show you what was the expression. Of course, when x, this is the way we're going to write it. X follow Bernoulli with a parameter p. Okay, the probability of that is basically going to be equal p raised to power x, 1 minus p raised to power that, x start from 0, 1. What I have now is what we call Bernoulli distribution. Okay, this is Bernoulli. Okay, x is actually the number of sources. Okay, p is the probability of success. That's why p is carrying x. The probability of success is going to have the number of success as its exponent. 1 minus p is the probability of failure. Okay, that you can also call q. Okay, because of the fact that the probability of success and failure has to be equal to 1. Success and failure are mutually exclusive. So X, the support of X, the state space in Bernoulli is basically going to be 0, 1, because the numbers of trials in Bernoulli equal to 1.
Is
This is what
one.
I mean by numbers of trials. You only try once, but in binomial, you try more than once. Okay, so what I'm displaying now on the on the screen is that of the binomial. Okay, you know, when k equal to 1, k is acting like an x, k and x. When k equal to 1, okay, in that expression, it's basically you're going to find yourself in Bernoulli. So which means binomial is a generalization of Bernoulli, and Bernoulli is a special form of binomial. Okay, now when we focus on binomial distribution, we want to look at how can we actually describe the distribution. When I want to describe a distribution, I want to know what is the shape of it. Does does the shape look like that of a normal distribution? Okay, I want to look at the center. When I talk about center, I'm talking about the mean. I want to look at the variability. Of course, if there is no variability in the process, the idea of computing the mean is out of place. We only calculate the mean in stochastic world, in a probabilistic world. Now, this is it. When when a random variable x follow binomial distribution, we expect that random variable x to have the mean. That mean is what we call expected value of x. Expected value of x means the average of x, or we call it the expectation of x, which we call NP, the product of the numbers of trial multiplied by the probability of success. We're going to derive this today. Okay, then the standard deviation is the square root of what you are seeing. Without the square root, that will be called variance. Okay, now
Yeah.
I know I've introduced. Someone want to ask a question?
Oh no, my bad. Sorry. I got
Okay.
the notes right here. I'll mute
Oh,
myself.
okay.
My bad.
Okay. Now, if you take a look at that is what binomial is all about. Okay, I gave you some example the other time. Binomial distribution is about when I have certain numbers of trials. Okay, how many success do I get? The success is going to be denoted as a random variable x, and of course, we also want to figure out what is the probability associated with that. Now, let me tell you this. I'm going to use an example from United States. We have states in the United States. You can partition region in the United States into like 4. I know we got Midwest. In the Midwest, we got some states in the Midwest, like Minnesota, Michigan, Wisconsin. Okay, those are the states in the Midwest. We have some states in the East, and the Southeast, and so on, like Northeast, and so on, like that. Also, in when you talk about random variable, a random variable can either be discrete or continuous. If a random variable is discrete, then it will follow discrete probability distribution. If a random variable is continuous, it will follow continuous probability distribution. Now, what are the discrete type probability distribution? One of the discrete type probability distribution is Bernoulli, binomial, geometric, negative binomial, Poisson distribution. Okay, those are probability distribution of the discrete type. The same way you're going to say, what are the states in the United States that are in the Midwest? Does that make sense now? Okay, so these are categories of that distribution. So if I'm talking about random variable and it is discrete, of course, you know what we mean by discrete, then it could have different type of probability distribution. It could be Bernoulli, it could be binomial. Now I just give you an example of what binomial is talking about. The binomial is saying that, okay, when I try more than one times, okay, how many success do I got? Okay, that's what binomial is talking about. And you know what? The possible outcome in binomial is two. And that is why we say it is categorized by dichotomous outcome. But let's come to geometric. What is the idea behind geometric? The idea behind geometric is how many times am I going to fail before I succeed? That's what geometric is talking about. If I didn't go to basketball, maybe there was a game last night and I did not visit. And maybe and I come to class and I start asking, do you go to basketball game last night? And I start asking from every one of you. And somebody said no, 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 no. And somebody said yes. That is geometric. Now the question now is I needed to ask 5 people questions before I was able to get a favorable response. The favorable response in that regard is yes. I wanted yes. Okay, so the geometric is going to say, okay, how many trials or how many failures am I going to have before recording first success? First success. No, 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 no. Yes. That is, I'm recording success at the first time. That is what geometric talk about. Okay, now let's define the random variable x. Okay, so, but let me tell you this. In geometric distribution, there's Bernoulli. Why Bernoulli? Because your response is going to be yes or no. Does that make sense? That's why I said, suppose that repeated independent Bernoulli trial, repeated. I go from this person to this, I'm repeating. And when I'm repeating, there are two possible outcomes. Okay, now the probability of success P are to be performed, and let X be the numbers of trial needed until the first success occur. The way we define X in geometric is different from the way it is in binomial. In binomial, X represent number of successes from a given numbers of trials. But in geometric, X represent the numbers of trials I needed to have before I will record the first success. P is the probability of success. And what is the probability mass function for geometric distribution is what I'm displaying on the screen. Okay, the probability of x equal to x is going to be equal to 1 minus p raised to power x minus 1 p. And what is the state space of geometric? The state space of geometric is going to be 1, 2, 3, because at least I must ask questions from one person. Do you go to basketball game last night? I don't know where to stop. I'm going to continue to go until somebody say yes. And that is why the support is going to go to infinity. Does that make sense? Okay, now we're also going to prove all this today. Now, if random variable x follow geometric distribution, and I needed to know on average, what would be the numbers of trials that I'm actually going to perform before I will record success. That formula is expected value of s, which is going to be 1 over p. We're going to derive that today as well. What is the variance? Because why do we need to find the variance? When you find the mean, when you find average, how do you tell about the reliability of the mean? How reliable is the mean? Then we need the variance and the standard deviation. And that is the expression for that. We're also going to derive that. But you know what? Before we derive that, I want to walk you through an example of geometric distribution. The probability of a successful optical alignment in the assembly of an optical data storage product is 0.8. Go ahead. Discrete random variable. So somebody asked whether geometric apply only to discrete or continuous, because before something can be discrete, then the random variable must be expressed as a whole number, a discrete. But for continuous, then it has to be in an interval. That's a good question. Now, but we have some distribution in continuous distribution that have a relationship with discrete. We're still going to talk about that. Does that make sense? It's just like state in the Midwest having relationship with states in the Northeast. Does that make sense? We're going to talk about that. Okay, assuming the trials are independent, what is the probability that the first successful alignment require exactly 4 trials? In a probability question, we're not going to tell you whether you're going to use binomial or Bernoulli or geometric. You will be the one that will figure it out. Look at that. What is the probability that first successful alignment require exactly 4 trials? That should be geometric. Okay, before you record the first successful alignment, you need to do like exactly 4 trials. At times in hospital, you know, they normally have more than one operation before they could correct what they want to correct. Okay, now what is the probability that the first successful alignment require at most 4 trials? At least 4 trials. There's a difference between at most and at least and exactly. When I say exactly 4, that means S equal to 4. When I say at most 4, it must not exceed 4, but it can go lower than 4. Okay, at least 4 we mean 4 and above. Take a look at the way it's interpreted now. Do you know what am I using now? I'm actually using this guy. I'm using this guy. The probability, because this is a probability mass function, okay, of of geometric. This is what I'm using now. I have to know my P. The P has already been given to be 0.8, right? What is the probability of the first successful alignment require exactly 4? Exactly 4 will be X equal to 4. I know my P, then I know my X, then I'm good to go. Okay, I'm just going to plug that in. That was what I did. Yeah, look at that. S equal to 4, I plug that in. Okay, now the other one said at most 4 will be 1 to 4. Don't forget, geometry start from 1, right? Okay, let's say at most 4. Okay, you're gonna compute when S equal to 1, use this formula. When S equal to 1, get your result. When S equal to 2, get your result. When S equal to 3, get your result. When S equal to 4, get your result. They add them up. That gives you 0.9984. Okay, and at least 4. At least 4 is going to be probability of S greater or equal to 4. But don't forget, 4, 5, 6, or infinity. That is going to take forever. Then we have a formula that we can use. Okay, because in statistical analysis, the probability of S greater or equal to A plus the opposite must be equal to 1. So if I want to get this, I can just do this. 1 minus this. Because we're dealing with S greater or equal to 4, S greater or equal to 4, then I'm going to do X less than 4. What are the X less than 4? 1, 2, 3. Okay, that's why you're going to do 1, 2, 3. Okay, you're going to use that probability to find one, then you add them up, then you subtract from 1, then you're basically going to get that 0.008. Okay, this is another example. Okay, assuming that each of your calls to a popular radio, if there's a program going on radio and you want to make your contribution, okay, a lot of people are calling at the same time. You are not the only one calling. Okay, when you try to call for the first time, okay, your call may not connect because there's a lot of people calling. And the question now said, assuming that each of your calls to a popular radio station has a probability of a 0.02 of connecting, that is of not obtaining a busy signal calls are independent, what is the probability that your first call that connect is your 10th call? That's a geometric question. What is the probability that it requires more than 5 calls for you to connect? Then what is the mean of numbers of calls needed? Because you may want to know, okay, on average, how many calls am I going to make before my call we connect? Then with that, we're going to find the expected value of S. Take a look at that is the solution. S equal to 10, you plug in 10, you already know your P, and of course, you know the probability function that you are using. every probability distribution as a function, just like every state as a map, right? Minnesota as a map, Wisconsin as a map. The map of Minnesota, even though Minnesota and Wisconsin, they are in the Midwest, they don't have the same map, MAP. Does that make sense? Therefore, even though geometric and binomial, they belong to discrete type probability distribution, they don't have the same function. Okay, take note of that. Now, well, if you take a look at what I use, expected value of x, expected value of x in geometric is 1 over p, and your p is 0.02. There's going to be 1 divided by 0.02. That was why you have 50. Okay, so take a look at all of that. Okay, now I want to go into negative binomial. Now I need to prepare your mind. If binomial is a generalization of Bernoulli, then negative binomial is a generalization of geometric. I'm going to say that again. Bernoulli and binomial, they address the same thing. You know what I'm trying to tell you now? Geometric and negative binomial, they are addressing the same thing. But what is it different? I'm going to tell you now. Okay, when I was talking about geometric the other time, I said how many trials am I going to have before recording the first sources? That is geometric, right? Now geometric is, do you watch the basketball game last night? No, 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 no. Yes, that's a geometric, right? Now I'm going to demonstrate negative binomial to you now. Do you watch a basketball game last night? No, no, no. Yes, yes, yes. Got a lot of yes after some series of failures. That's a negative binomial. What is the difference now? It's R. Look at R. When R equal to 1, if you take a look at that expression for negative binomial now, okay, which means the difference between negative binomial and geometric is in geometric, first you talk about first success. In negative binomial, you talk about root success, not just one. Okay, now when you take a look at the expression now, the probability of this equal x minus 1 combination this and p raised to power r of minus 1, then you got 1 minus p raised to power x minus r. If you take a look at what I have now, this is negative binomial. You know what? Let us set r to be equal to 1. If r equal to 1, okay, if this is 1, this is going to be combination 0 is going to be 1. Okay, if r equal to 1, okay, you basically let me see. Oh, sorry. I'm using the second one. There are two versions of negative binomial. This is the one I'm using. I'm using the second one. X minus 1, r minus 1, p raised to power r, 1 minus p raised to power x minus r. I'm using the second version, this version here. Now here, when r equal to 1 here, okay, when r equal to 1, what does it give? Let's see. When r equal to 1, okay, it's going to be this combination 0. That's going to be 1. P, okay, 1. What is this? This is geometric. This is negative binomial. You see that, right? So this is a general form of that. And you know what? Look at the mean, r over p. When r equal to 1, that becomes the mean of a geometric. Don't forget, the mean of a geometric is 1 over p. But the mean of negative binomial is r over p. Okay, when r equal to 1, the mean of negative binomial becomes that of geometric. The same thing applicable. Look at the variance and the standard deviation. Take a look at that. Okay, now that's about. Now let's look at you know, example under negative binomial. Suppose S is a negative binomial random variable, but let me tell you this. I'm not going to tell you, suppose S is a negative binomial. You be the one that will figure it out. Maybe based on the way I said the question, I say, okay, the your phone connect at the third, maybe the third time your phone connect occur a day. So definitely you need to be able to identify what your R is. But let's say for instance you're given this parameter P and R. How do you determine questions under negative binomial? Okay, this is the way you're going to proceed. Just going to make use of the probability mass function for that. Okay, now you know what I want to do now.
Okay.
Yeah, go ahead.
So I'm just wondering, is the R, um, is it like the number of successes after first failure, but not the total amount of successes?
Okay, you're referring to R, right?
Yeah, like, is it like, okay, with your basketball example, is it like
Yeah,
no, no, then if it was like three yeses after that, and then another no, and then another yes, would it be four or would it be three for the R?
that's a very good question. What we're trying to say, the idea is just this. Um, let's say, for instance, somebody, it's not the first time we're tasting sauces. Okay, at times we could have like just like what you said. When I could have like no, 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 and I have yes, yes, and I still have followed by some no, and I later have yes. Okay, now the yes that I'm getting now is not going to be the first yes. The fact that there have been some previously existing yes, that make it a negative binomial. Does that make sense?
Yeah,
So which means we are not seeing success for the first time. So
okay,
that is what negative binomial implies.
okay,
Does that make sense?
So R equals the total number of successes that are observed.
Exactly.
Thank you.
So that is what R equal. And if R equal to 1, then you are no longer in negative binomial. You are now in geometric.
And you're
Okay.
just cool.
Okay,
Thank
go ahead. Go ahead.
Well, I was just gonna say yes. So with Bernoulli, when you just have one, you're just gonna find that first success. And negative binomial is to figure out how many total successes you have over your trials.
Exactly.
Thank you. Cool.
You're welcome. Now, what I want to talk about now is walking you. I'm going to stop the share and we're going to do some derivations now. The derivation is going to start from Bernoulli. I'm going to touch Bernoulli. I'm going to touch binomial. I'm going to talk negative binomial. What do I want to do? I want to make a derivation for the mean and variance of each distribution. Of course, what we're doing now is actually has to do with the theory of statistics. Okay, so what I'm going to do now, I'm going to stop here. I'm going to stop my share. I think I've already done that. Then I'm going to share my whiteboard because I know those in class may not be able to, like those sitting at the back. So because of that, I'm going to share my whiteboard. I need everybody to confirm. Wait a minute. Why is whiteboard not displaying in the class? I know those online can see the whiteboard, but let me see why those in class are not seeing the whiteboard. Give me 1 second. Let me see if I can, if there's a way I can do that. Okay, I'm gonna do this now. Those of you at the back, you can see the board, right? Okay, thank you so much. And those of you online, can you also see the board? I'm talking
Yes.
about the whiteboard. Okay, thank you so much. Now, I need everyone to pay attention. Now, what I'm going to be doing now, apply mathematical knowledge. Okay, well, I want to start with Bernoulli. Okay, Bernoulli distribution. X follows, when you say this, I'm talking about if X, this guy means X is distributed Bernoulli with parameter P, and of course, the probability of X equal to X, okay, is basically going to be P raised to power X, 1 minus P raised to power that X start from 0 to 1. Now, this is a probability mass function. We call it probability mass function of a Bernoulli distribution. Now, how do I show that this is a valid PMF? Okay, it's just like somebody says, show, how can we prove that this very state is a state? Does that make sense? Okay, now, because it's a discrete, we expect that when we sum that over the state space, it must give us 1. Okay, now let us now try that and see whether it's going to give us 1. So summation S star from 0 to 1. What is the distribution? This guy, right? P of X, 1 minus P raised to power 1 minus X. Okay, now we're gonna put P raised to power 0, 1 minus P raised to power 1 minus 0 plus P raised to power 1 and 1 minus 1. Okay, I wanted to take a look at what we actually have right now. Okay, now, you know, we have P raised to power X, 1 minus P raised to power 1 minus X, and we want to sum it. Now, you know, we have P raised to power 0. That, so this is going to be 1. This is going to be 1 minus P plus P, because this guy raised to power 0 is 1. So what do we have? Now, we've already proved right now that this is a valid PMF. Okay, what if I'm seeing me time 2 here? Show that this particular given probability function is a valid probability function. The only way it can be a valid probability function is when, if it's a discrete, when I sum it over the state space, it must be equal to 1. Okay, now, after that, the next thing now, how do we derive the mean? How do we derive the mean? We want to find the expected value of X. Expected value of X for discrete type probability distribution, of course, is going to be this. For Bernoulli, S star from 0 to 1. So I'm actually going to have X. What is the P of X in Bernoulli? P raised to power X, 1 minus P raised to power 1 minus X. Then I'm going to have 0, P0, 1 minus P raised to power 1 minus 0 plus 1, P raised to power 1, 1 minus P raised to power 1 minus 1. Of course, because of 0 here, the whole thing here is 0. That's a P, right? And this is going to be raised to power 0, 1. Finally, I got P. Now, what have I derived now? Anywhere in the world, the mean of Bernoulli is P. This is how we derive that. Okay? Now, if I derive the mean to be that, I want to derive the variance. I want to derive the variance. The variance of X is defined as expected value of X squared minus expected value of X all squared. This is expected value of X. What this guy is trying to tell me here, I should square it. But how am I going to get expected value of X squared? I'm going to write expected value of X squared is going to be, for discrete, S squared Now I needed to see this. When I was talking about expected value of x, what do we have here? X. When I'm talking about expected value of x squared, what do I have here? S squared. You see that now? Now, here, I'm going to have 0 to 1. Okay, now I'm going to start plugging in. When s equal to 0, 0 squared, or before plugging in, let me first s squared. What was the p of s? Is p raised to power x 1 minus p raised to power that. Now, 0 that's 0, p0, 1 minus p, 1 minus 0 plus 1 squared, p raised to power 1, 1 minus p raised to power 1 minus 1. So this is going to be 0. And I'm actually going to have p. Expected value of s in Bernoulli is p. Expected value of s squared equal to p. Now, what is the variance of s? Now, the variance of s is going to be, this guy is p minus the square of minus this. So this, if you factorize, you're actually going to have this when you factorize. And this can also be written as q. Look at that. That is the variance. If this is the variance now, the standard deviation of x is the square root of the variance of s, which is going to be square root of pq. This is all about Bernoulli. Do you know with this you can generalize for binomial? If the mean of Bernoulli is this, then the mean of binomial will be np, n. Because here, when n equal to 1, you go from binomial to Bernoulli. So if I want to make a kind of generalization now, okay, if I want to make a generalization, I'm actually going to say when x followed by binomial with parameter np, where the probability of x equal n combination x, p raised to power x, 1 minus p raised to power n minus x, s start from 0, 1, 2 until you get to n, then the mean is going to be np because the mean of Bernoulli is p. Then the variance of Bernoulli is going to be npq because the variance of Bernoulli is pq. And when n equal to 1 in binomial, that will lead us to Bernoulli. And I can also generalize about what the standard deviation of binomial is going to be. The standard deviation of x is going to be square root of npq. So if I know the standard deviation of Bernoulli, okay, I can generalize on the standard deviation of binomial because the two of them are distinguished by the numbers of trials. The numbers of trials in Bernoulli is 1, but the numbers of trials in binomial is more than 1. Therefore, binomial is a generalization of Bernoulli. Does that make sense? Now, I need you to also see something like this. We normally write this. X follows Bernoulli with parameter P. Okay. Now, do you know that Bernoulli with parameter P can, P is the same thing as writing Bernoulli with parameter 1 comma P. 1 comma P. 1 here means I'm talking about n is equal to 1. But in the case of binomial, we normally write NP, which means n is more than 1. N is not 1. But the moment n equal to 1, you are no longer in binomial, but you are in Bernoulli. Okay, I want to go to geometric. I want to go to geometric distribution now. Some of you may be wondering, why are we doing what we're doing now? There's a reason why we do what we do now. Without mathematical knowledge, there is no way we will be able to have a formula for how do we figure out the average in Bernoulli? How do we figure out the average in binomial? How do we figure out the average in geometric? And that's what I'm walking you through now. And this calls it theory of statistics. So theory of statistics requires that you need to be able to know some basic, like, what is behind the scene? Why do we have this formula to be this formula? Now I'm going to go into geometric now. Now, the other time I actually use this because we have different of them. So 1 minus p raised to power x minus 1 p, the probability of x equal to this. Okay, for geometric. I want to work on geometric now. Okay, you know, when a random variable and the state space is x1, 2, 3. Okay, this is the PMF of geometric distribution. Okay, now if this is the PMF of geometric distribution, okay, and if I want to rewrite that in a short form, I can actually write this. I can write this. X follows geo with parameter p. When I say geo with parameter p, I mean geometric. Does that make sense? Now, we want to find the mean. We want to find the mean. And at the same time, the way we investigated the other time about whether this is going to sum up to 1, you can also do that. But I want to quickly, because of my time, I want to quickly go to, deriving the mean of a geometric. You know, the mean is 1 over p, right? Let us derive it. I need you to pay attention now, okay? Now, summation, s start from where? 1 to infinity. Please take note. You need to know the state space for a particular distribution, okay? Now, x, probability of x equal to that. So which is going to be x start from 1 to infinity, x, 1 minus p raised to power this. Look at that. We have that now, right? Now, when you have that now, you need to simplify. You need to simplify. Expected value of x equal. Okay, you are summing with respect to x. This is a constant, right? This guy can come outside here, right? You're going to have p summation x start from 1 to infinity x. Now, 1 minus p. Recall that 1 minus p equal to q. P plus q equal to 1. Okay, so I can rewrite that as q raised to power this. Take a look at that. Now, I needed to look at this. This is the same as this. You see that? What is the derivative of q with raised to power s? This is going to be the result. When you have q raised, like for instance, you have x raised to power 2. What is the derivative? That's going to be 2x2 minus 1, which is 2x, right? If y equal to this, what is the y ds? That's what I mean. So when you take a look at this, the way it look like, it means it is the derivative of with respect to q of x. So if I want to rewrite that expression now, okay, if I want to rewrite this expression now, you know what I'm going to do? I'm actually going to write p this s start from 1 to infinity d dq q raised to power x. This guy now is replacing this guy. You know what I'm going to do now? Bring this guy out. Bring that guy out. P d dq. I'm going to be left with this. Is that not? Oh, when I'm left with this guy now, what am I going to do now? P d dq. You now bring this guy out. Bring that guy out. P d dq. I'm going to be left with this. Is that not? Oh, when I'm left with this guy now, what am I going to do now? P d dq. This guy mean Q1 plus Q2 plus Q3. You remember what you did in high school? Sum to n time of a geometric series. That's a geometric series. Okay. What is the formula for sum to n time in geometric series? Okay. When you have sum to infinity for geometric series, it's going to be first time over 1 minus common ratio, right? What is it? What is the first time? Q. What is the common ratio? Q. Because Q squared divided by Q is going to be Q, right? Q raised to the power 3 divided by Q squared is going to be Q, right? Now, if I want to rewrite this guy now, then I'm going to have expected value of S equal P d dq, okay? Then applying this is going to be Q over 1 minus Q. You know what I want to do now? I want to differentiate this guy. I want to differentiate this guy now with respect to Q. Has anybody heard about quotient rule in mathematics, calculus? We are now applying the calculus knowledge now. Okay. Now I want to differentiate this guy. So expected value of X equal P. Now you remember what I'm going to do. If I want to differentiate this guy, I'm actually going to you remember V du the Q minus U dV dQ divided by V squared. This is a quotient rule in calculus. Okay, now this is acting as my U, this is acting at my V. So what am I going to have? So expected value of X equal P. Now V, I'm going to write 1 minus Q. The U dQ, differentiate 1 minus Q with respect to Q. That's going to be negative 1 minus, what is U? U is Q. Then what is the V dQ? Okay, the V dQ is negative 1. Now let's take a look at this again. V, 1 minus Q. Okay, then what is the U? Oh, sorry, the U dQ is 1. Because I'm differentiating this guy. That's 1. Okay, minus what is U? Q. What is the V? So divided, what is the V squared? 1 minus Q all squared. So what do I have now? P into 1 minus Q minus that. That's going to be plus Q, right? Divided by 1 minus Q all squared. This, cancel that, right? If that guy cancel that, I'm actually going to be left with P, 1 minus Q squared. What do I call 1 minus Q? P, right? So this is going to be P divided by P squared. This reduce that. What do I have generally? 1 over P. That is the proof that the expected value of X is 1 over P. You can go on and derive that of the variance. Okay? Now, what I've just shown you now is a theoretical development of this. And that is required in this course because this course is called the theory of statistics. Okay? We're going to continue from another distribution tomorrow. Is there any question at this time? Is there any question at this time? Once again, if there's anyone struggling in this class, please reach out.
I got
Go
one
ahead.
quick question, just because I'm not able to read exactly, but right behind you, if you look, what is that? The S of infinity equals, is that A or X right above that Q?
Is it the one where I'm pointing?
Nope, right down and to the right. That S infinity equals, yep, right there.
Oh,
Equals,
okay. This one is from your calculus knowledge
yep.
of sum to infinity in geometric progression. So sum to you've heard about geometric series, right?
Yep.
Yeah. If you are summing a geometric series, that doesn't terminate. So the formula for sum to infinity is going to be first time A divided by 1 minus R. R here is a common ratio.
Thank you.
You're welcome.
Awesome.
Any other question from anybody? Okay, this, like I said, this is where I'm gonna stop today. Make sure you all stay safe and have a lovely day. Bye for now, everyone.
I have a quick question for you.
Yeah, go ahead.
So when we were talking about I think like the probability mass function, and you said that when you have to solve it, it has to equal 1.
Oh, you mean you said when I'm talking about probability mass question that s equal to 1? Is that what you mean?
Yeah, does it always have to equal to 1, or can it equal like a different number?
That's a very good question. And that is the reason why you need to know the state space of a particular distribution. For instance, if I'm talking about uh, geometric distribution, my x is going to start from 1.
Okay.
Don't forget, the x here represents the numbers of trials.
Mm-hmm.
X in geometric distribution represent the numbers of trials I need to do before I record the first sources. So S is going to start from 1. But if I'm talking about Bernoulli, X is going to start from 0 and end in 1. You know why we start from 0 and we end in 1? Because the numbers of trials in Bernoulli is 1, and X in Bernoulli means numbers of successes. If I try once, it's either I see 0 success or 1 success, and that is why the state space of Bernoulli will be 0, 1. But for
Okay.
binomial, it's going to be more than that. Binomial is going to be S start from 0, 1, 2 up to N. Does that make sense?
Yeah, so like I was looking at like the assignment that's due for this upcoming Sunday, and I'm looking at question 3, and like while you were talking about it, I was trying to like do it myself. So like for 3A, you want us to like show that that the
Let me,
QF given is a valid probability function. How would you like us to show that?
okay. Before I will understand what you do, I'm going to do something now. I'm going to go back to the assignment. You said question number 3, right?
Yep.
Okay, give me 1 second. Basically want to, so that we're going to be on the same page. Okay, I just opened the assignment 3 now. You said question number 3, right?
Yep, 3A.
Okay, now when you take a look at 3A, the 3A is f of s equal to x over 15. That's a discrete probability. How do I know it's a discrete? I know it's a discrete because the state space is 1, 2, 3. The situation where the state space can be expressed as whole numbers. Of course, I'm talking about discrete function. Now, what I want you to do in A, show that PMF given above is a valid probability function. You're going to do it the same way we do it today, where we're going to do summation of f of x. Does it equal to 1? When I say summation of f of x here, you know what I expect you to be doing? Plug in 1 into x. That would be 1 over 15 plus
Yep.
plug in 2 until you get to 5. Then add them up. Does it give 1? That's what I'm asking.
Oh, okay, sounds good.
Okay. So the moment you give 1, then it's a valid PMF. And after that, then you can proceed to get the expected value of s, expected value of s squared, or whatever you want to get. Does that make sense?
Correct. So when we're doing A, that has to equal 1, but like when you're doing 3B, 3C, and 3D, that does not have to equal 1, correct?
Exactly.
Okay,
Exactly.
sweet.
But
Okay.
you know what? For B, C, and D to be correct, A has to give you 1.
Okay.
If A doesn't give you 1, then whatever we're going to be computing from that, because that is telling us what that is telling us that, okay, this function is not a probability function. Because we expect the probability function, we expect the total area under a curve to be equal to 1. The moment it does not, then whatever inference that we want to derive from it will not be valid.
Okay. Sounds good.
Okay? Is
Yep,
that
that makes
all? Is
sense.
that all your question?
Yep, that makes sense. Thank you so much.
You're welcome, and have a good day.
Yep, you too.